Okay, in lab number 16, we're going to use seismograph data to figure out the epicenter or location where an earthquake happened. And when the earthquake occurs, there are two types of waves generated in the Earth's crust. Primary waves are the ones that arrive first, and secondary waves are the ones that arrive next. Secondary waves always travel slower, so the further away you are from an earthquake, the arrival time between the primary wave and the secondary wave will increase. Now this is shown in the graph on the second page. As you can see, as the distance away from the epicenter on the x-axis in times 10 to the third kilometers, so 0, 1,000, 2,000, 3,000 kilometers, as you get further away from the epicenter, this arrival time between the primary wave and the secondary wave gets larger. Okay, and it's this wedge in between the P and S wave that we're going to use to figure out how far away earthquakes happened and where they were located. Now, the first thing that we're going to need to do is to create a little ruler. This ruler will help us figure out exactly where on the graph certain times occur. So we're going to take a scrap piece of paper and lay it down next to our graph, right here on the edge. Now the largest time difference between the P and S wave, according to our graph, is right here at the edge. So we're going to use that as our ruler. So we're going to start right here, and that's going to be 0. Okay, this is minutes between the arrival time. So 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll go on up to 11. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Now in between each of these is 60 seconds. 60 seconds is a minute. And there's 3 blocks, 1, 2, 3. So each of these blocks, 20, 40, and 60 seconds. So each block going up on the y-axis is 20 seconds. And that's going to be important for us to remember. Okay? So, once we've got our ruler made, we can start answering some of the questions about these earthquakes. Now, on the first page, it does a few simple, a simple graph analysis. So, what is the difference in arrival time in minutes and seconds between the P and S waves for an earthquake with an epicenter 2,000 kilometers away? Okay, so we find 2,000 kilometers, which is 2 on the graph, and we're just going to count how many minutes and seconds are in between the P and the S wave right here. So we got 1, 2, 3 minutes and 20 seconds. So 3 minutes and 20 seconds of difference in arrival time is an earthquake that's 2,000 kilometers away. Okay, we can also do this backwards, which is what we're going to have to do next. So the difference in arrival time of P and S wave, which is 4 minutes and 20 seconds. Okay, so we're looking for now on the graph where 4 minutes and 20 seconds, right here, okay, is going to line up with our graph. So we start out here at the bottom, okay, and keeping the ruler vertical, we're going to move it up until the 0 line always stays on the P, okay, and the S wave lands on our mark on our ruler at 4 minutes and 20 seconds. So an earthquake that has an arrival time that is 4 minutes and 20 seconds apart is going to be 3,000 kilometers away. Okay, so that's the basic of how to use this graph. Okay, it gets a little bit more complicated when we actually look at seismograph data. So let's take a look at seismograph data for earthquake A. Okay, we've got this data and then a chart at the bottom. The chart wants to give us the P wave arrival time, the S wave arrival time, and the difference in the arrival time. And then we're going to use the graph to find the distance away. Now, we're going to cheat a little bit here and only look at the difference in the arrival time. We don't really need to get the first two parts of the chart. We don't really need the times, because that's just there to give us the ability to subtract, and we can do this on the chart itself. So let's zoom in on seismographs A for New York. Focus, camera. There we go. All right, now we've got it focused. Okay, so seismogram A from New York is the P wave arrival times at 12 hours and 17 minutes and 0 seconds. Okay, and each of these hash marks that are labeled is 1 minute. See, this one goes to 12 hours, 18 minutes, 0 seconds. 12 hours, 19 minutes, and 0 seconds. So the time between the P wave, which is the first large peak, and then the S wave is 2 minutes. So let's just write 2 minutes here. That's the difference in time between those. Now you can also put that down in your chart. Down here, for New York, we have a difference of 2 minutes. Okay, then we're going to look at Houston's seismograph data. It arrives at 12 minutes and 18 seconds. So the earthquake, we already know, is further away from Houston than it is New York. And it arrives at 12:18, and the S wave arrives at 12:20, and 1, 2, 3, 4 of these hash marks in between 12:20 and 21. Now there's 1, 2, 3, 4, 5, 6 marks between each. So each of these marks is 10 seconds. Okay, so 12:18 to 12:19, that's 1 minute. 12:20, that's 2 minutes. And then 1, 2, 3, 4 of these hash marks. So our arrival time here is 2 minutes and 40 seconds. Okay, so let's put that down in our chart for Houston. 2 minutes, 40 seconds. Okay, now let's look at the very last seismograph data. This is for Miami. P wave arrives at 12:18 and 1, 2, 3, 4. Okay, so 12:18:40. And then the S wave arrives at 12:22. So we can count from this block to here. That's 1 minute, right? Okay, 2 minutes. 3 minutes and 1, 2. 3 minutes and 20 seconds. Okay, if you didn't see what I did there, I just jumped from the same spot here between those two hash marks to the same spot between these two. So that's 1 minute of time between the mark where the S wave, P wave arrives, the mark where the P wave arrives, 1 minute from there, 2 minutes from there, 3 minutes from there, and then there's 2 little marks to get to where the S wave arrives. So from Miami, there's 1, 2, 3 minutes and 20 seconds of time. 3 minutes, 20 seconds. All right, so now is where we're going to take this data and look at the graph. Okay, now our very first time was 2 minutes exactly. So we're going to find 2 minutes on our scale, our little ruler here, and we're going to look at on this graph where if we keep the P wave at the 0, where the S wave lines up at 2. Okay, so we're going to go down until we meet that mark. All right, and that's right about right there. So we've got 1,000 and some odd amounts right here for the first one. Okay, so there's 1,000 to 2,000. There's 1, 2, 3, 4, 5 marks in between. Okay, so that means that that one block is 200. So our distance to the epicenter here is 1,200 kilometers away. Okay, so that means that the earthquake happened 1,200 kilometers away from New York. Now we need 2 minutes and 40 seconds. Okay, so now we're at, remember each of our blocks here are 20 now, so we're going to go to 2 minutes and 40 seconds. We already know it's going to be more than 1,200, so let's start there. And moving up. Okay, right here is our mark for the difference in arrival time of, oh, let me go back actually. Yeah, this is better. I was on the 3 instead of the 2 minutes and 40. So be very careful with your ruler to make sure it's correct. So actually right here is the better mark for Houston's time. Okay, so that's 2, 4, 6. So that's 1,600 kilometers. Mark that down for the distance, 1,600 kilometers. Okay, and now we need to do the Miami number, which was 3 minutes and 20 seconds. Okay, so now we're up to 3 minutes and 1 block, 3 minutes and 20 seconds. Okay. There's not much difference here, so that would be right about there. 3 minutes, 20 seconds, 0 on the P, 3 minutes and 20 on the S, so that's 2,200 kilometers. Alright, so now that we have our distances, we can plot this on the graph. And now here's where it gets interesting and a little fun. You'll need a compass to do this. Not the compass to find your direction, rather, a compass to draw circles. You'll take and put the point of the compass on the city from where the seismograph was read and draw a circle the same same radius as your distance that we figured out from the graph. Okay, so let's take a look at this on the actual map. So we're going to flip it over. I'm going to write down our measurements here so I can reference them. Okay, New York is 1,200. Houston is 1,600. And Miami was 2,200. Okay, so let's flip over to our map A. Okay, now at the top, of course, we've got the United States. If you don't know the orientation of the United States, up is north here, down is south, east and west, and we have a scale bar. So each one of these scale bar marks is 100 kilometers. And our first city was New York, and it was 1,200 kilometers away from New York. So we're going to take our compass, placing the point on 0, we're going to open the compass up to 1,200 kilometers. Okay. Now the trick with this is to be as precise as possible without letting the compass move around while you draw your circle. So this compass is a little better than the plastic ones that you might have for this. The plastic ones, if you kind of hold them like this and then move the paper around under the compass, it works a little better. So I'll show you how to do that. Again, we're at 1,200 kilometers away, so you're going to put the point of the compass under, or rather on, New York, and then you're going to spin your paper around underneath the compass. So it's easier to spin the paper than it is to spin the compass. Okay, and as long as your compass didn't move any, you should have drawn a nice perfect circle. Okay, so with one seismograph set of data, or one set of data from one seismograph, we know that the earthquake happened somewhere around on that circle. Okay, but we need 2 more circles to narrow it down. let's look at our Houston measurement. Houston, Texas here, it was 1,600 kilometers away. So we are going to open up our compass now to 1,600, not that much bigger than the one before. Okay, and put it on Houston, and then draw your circle all the way around Houston. Alright, so now we've got our location of this earthquake narrowed down to 2 points. Okay, 2 circles intersecting at 2 different points. That helps narrow down where that earthquake happened. It either happened out here in the Atlantic Ocean or happened right here next to Chicago. We need a 3rd circle to finish triangulating this location. Okay, triangulate has tri in it, which means 3. Okay, so that's how many circles we have to have, is 3. So our Miami point was 2,200 kilometers from the earthquake. So we need to open up our compass to 2,200. Now, our scale only goes up to 200, but we know that each one of these blocks is 1, so we can use a ruler to measure out how far it needs to go. So that looks like 3. Okay, looks like the end of the line on the scale is 2,200. Okay, so 2,200. We're going to open up the compass all the way to that point. Okay, and we're going to draw our 3rd circle. Okay, now, you'll notice that my circle did not intersect at one specific point. Now, it's possible that our measurement for the Miami earthquake was wrong, so let's go back. Okay, 3 minutes, 20 seconds. 1, 2, 3, 20. Look at our graph again. Yep, that was what was wrong. So it's not 2,200. It's actually 2,000 at where I should have marked this. So I made a mistake, and that's part of troubleshooting this. Okay. Now, even with our mistake, we got pretty close. We know that somewhere inside this little circle, where these 3 circles intersected, was where the earthquake happened. But I bet if we go back and fix our measurement to 2,000, what it should have been. Okay, I bet when we do it off of Miami here, the circles will come together very nicely. Okay, still off just a hair, but it's a little closer. Okay, so this is the process that seismologists, those people who study earthquakes, actually use to figure out where earthquakes happen. Now, this is the old-fashioned way of drawing circles on a map and narrowing it down. But within this little triangle, where the 3 circles intersected, that's where this earthquake happened. Right outside of Chicago, or right on Chicago, depending on how your circles were drawn. It doesn't have to be exact for this lab, but get it pretty close. So what's really cool in reality is that now all of this is digital. Seismograph data is coming into the United States Geological Survey all the time, non-stop, 24/7, and computers are used to digitize that data and figure out where earthquakes are happening. So very quickly, seismologists can boot up their programs, look at the seismograph data from all over the world, and identify earthquakes. And with more and more data from more and more research sites, you can triangulate better where the earthquake was happening. So like our first failed attempt, where we got a really big area of where that earthquake may have happened, we could have taken maybe Seattle's seismograph data and done it. And we could have drawn a 4th circle from Seattle to try to triangulate a little better or narrow down our options. The goal is to get it as close as possible. Okay, so that's how scientists use the difference in arrival time of the primary and secondary waves to figure out where an earthquake occurred. So you needed to go ahead and do this for earthquake B and C. Earthquake C is a little different and it has a little bit different map, so you'll have to do that on your own. And then answer the questions, the conclusion questions at the end of the lab. You should be able to do that now with the information that I've given you. Okay. And that's how seismograph data is used to determine earthquake location.